As always, the views expressed during today's webinar are those of the speakers, not of Stratford, the speakers' firms, or clients, and are not intended to provide legal or tax advice. We have gathered an authoritative panel to examine how states are using statistical sampling to recover Medicaid overpayments. The panel will also provide guidance to counsel for health care providers on how to challenge the sampling results and the alleged Medicaid overpayment, leveraging lessons from Medicare cases. Our panel today includes David Ross, shareholder at O'Connell & Aronowitz in Albany, New York. He's joined today by Dr. Pat Maykuth, President at Research Design Associates in Decatur, Georgia. And David, when you're ready, we'll get started.
Sure. Thank you, Molly. Good afternoon, everyone. My name is David Ross. I'm an attorney. I practice Medicaid, Medicare, private insurance, audit issues, among many other practice areas. So today's presentation is going to be in two parts. The first part is going to be a primer on the legal issues in statistical sampling and extrapolation, a little bit of background information. We're going to talk about the role of an expert. And part two of the presentation will be Dr. Pat Maykuth presenting the nitty-gritty of the statistical sampling and extrapolation technical issues that you'll need to know in order to best represent your client who finds themselves in the position of being the subject of a Medicaid audit involving statistical sampling and extrapolation. So this is part one. We'll just talk briefly. What is sampling? Well, sampling is taking a subset of the universe of claims of the Medicaid provider for the purpose of auditing them. And it's very important how the sample is chosen. It needs to be chosen in a statistically valid random sampling method. And usually that involves computer software. And the key point here, and Dr. Maykuth will expand upon this later, the sample must be randomly selected in order to be valid. So what is extrapolation? Well, this is the reason why they're doing the sampling in the first place. And extrapolation just takes the results of the audited sample of claims and projects them to the entire universe of Medicaid claims during the audit period and arrives at what they will claim is the amount of overpayment that your client owes. So just a rule of thumb, and this is certainly not accurate, but assuming a 10% error rate in the sample, they would extrapolate that to the claims universe, and you would anticipate approximately a 10% error in the universe of claims. So that's the purpose. They're not required to audit every single claim in the universe. That would be too time-consuming. And they're allowed to do sampling and extrapolation, which is really what we're going to be talking about today. And here we cite from the Code of Federal Regulations. This is the rule that applies to the United States Department of Health and Human Services, which basically lays out the legality and what allows them in the Medicare program to use statistical sampling and extrapolation. So the requirements are pretty straightforward. If the sampling study is based upon an appropriate sampling and computed by valid statistical methods, it will constitute prima facie evidence, and the burden then shifts to the provider to rebut the findings of the government's statistical sampling study. So state Medicaid programs generally use a similar approach. The burden is on the provider, your client, to show why the state's calculations or process are in any way invalid or flawed. So looking at individual states, we've looked at several. Medicaid does not have a playbook like Medicare does. There is no universal guidance establishing the rules of the process in Medicaid. So, for example, Texas follows the Medicare rules and uses the RATSTATS computer software suite of programs for its sampling and extrapolation. California and Florida use generally accepted statistical standards. New York has no rules at all. So, again, the burden of proof is on you, the provider and provider's counsel, to challenge the statistical sampling and extrapolation process, and it's going to be presumed valid until you're able to successfully establish that there are problems with it. So what are the various legal and scientific issues? Well, they're very complex, and we don't purport to make each and every participant in today's conference an expert, but we are going to put you on notice of certain questions that you need to ask of your expert in evaluating what the state has done in your particular audit. And you may be wondering, do I really need an expert? Can I figure this out by myself? And my opinion is that you absolutely do need an expert. These are issues that are not intuitive, they're not common sense, they're not things that lawyers typically know. It would be no different than if you had a personal injury case and a motor vehicle accident, you would need to hire, an accident reconstructionist person. You really need an expert here. And if you look through the materials, you've probably already made that determination yourself, and if you haven't, you'll probably be at that point by the end of the presentation. So, absolutely essential, you need to have a statistical consultant for two reasons: to understand how the audit was conducted and whether the results are statistically valid. So I've always maintained that no one has enough training in statistics, generally as a lawyer. We've all probably taken some, at the undergraduate or maybe graduate levels, but we probably know just enough to be dangerous. So that's why we really rely on experts, and the expert is the only person who's really going to be able to properly answer the really important questions that pertain to the audit. So here are just some of the questions that you'll need to have answered by your expert. Is the process used properly designed? Very, very important question, and Dr. Maykuth will talk more about that as well as these other issues later on. But we're just trying to frame in your mind what the questions are before you get into the nitty-gritty. So was the process used suitable? And is the process as applied to my client proper? Is it different from the norm? If so, how does it differ? Why does it differ? And a key concern, how is the sample size chosen? Was that selection proper? Many states use the same sample size. New York is one of them, typically 100, sometimes 150, and even less often 200. How that number was arrived at is critically important. And is that number, the sample size, large enough for the confidence interval that you're being provided by the state for the accuracy of their estimation of the amount overpaid? Did the auditors properly document the audit? More questions. Is the software program used to generate the random numbers certified or widely accepted in the field for this purpose? Some states use programs that are not widely accepted or are proprietary. Was adequate documentation for replication of the results provided? So the key is that anybody should be able to look at what was done and replicate it. And if that can't occur, there's a serious problem with the process and the results used by the state. So was the software program used working as it was designed? Well, you don't really know until you have an expert look at the source code of the computer program. And this would not be necessary if they used a commonly accepted program like the RADSTAT suite or other well-established computer software programs, but some states don't use those. And this becomes very interesting, and it was very interesting in New York State. The source code was denied to providers, and an administrative law judge determined that this was a violation of due process, so they had to turn over the source code. And we had a case where we had an expert analyze that source code, and it turned out the software program was not working properly and did not work the way the state's expert testified that it did work. So that was a very key finding, which we would not have known had we not retained, an expert to look at the computer source code. So how were the random numbers selected? Were they generated by a valid method? So whether or not the numbers generated during the audit process are random or not is something that may be tested. There are tests for randomness which may be applied to the numbers that were used to choose the claims to audit in the sample. So Dr. Maykuth can talk a little bit about that later. And again, this replication issue, very, very important. If the results can't be replicated, then something happened which should invalidate the process, because this is mathematics and statistics, and these things should be replicable. So the seed is a very important issue here with some software programs. The way they operate is a number is input into the program to generate a list of random numbers. So if you have that seed and the program, you ought to be able to input that number, that seed, into the program and get the exact same output. And in some instances, in New York, for example, for many years, the seed was not retained by the state Medicaid auditors. So you had no ability to test their computer software because they failed to retain the seed. And another issue was, is the frame sorted as it was at the time the random numbers were used to pick the sample? So there are any number of ways to arrange a universe of claims. It could be by date of service, it could be by amount, it could be by procedure code, it could be by recipient. However it was arranged, you need to have that arrangement in front of you when you evaluate when the random numbers were applied to the frame, what particular claims were chosen as a result of that superimposition of, for example, a random number of 319. You apply that to the universe of claims, the frame, and line 319 in your universe would be the claim that was selected for audit, and that became part of the sample. If it was arranged in a different manner, line 319 would be a different claim altogether. So you need to know how the frame was sorted at the time the random numbers were applied to it. There are other issues. What about the extrapolation calculations themselves? They typically were not provided with the calculations. Sometimes they're simple, sometimes they're not. So without the calculations, you don't know if they were done correctly or properly, and it's something that needs to be looked at. So these studies often have the right idea, but wind up with the wrong answer. So if we look at this cartoon, vote for me as president of the math club. And there's a little chart there. And 21% of the boys and 30% of the girls support this individual for president. And the conclusion is, since 21 and 30 are 51%, this person thinks he or she will get 51% of the vote. And this is clearly the wrong answer, because that's just not how this would actually operate. So a most classic case of the failure of statistical sampling and extrapolation is the Dewey-Truman presidential election, where individuals who had a telephone were the only individuals who were surveyed when they conducted this poll. So if you didn't have a telephone, you were not part of the survey. So of those folks that were surveyed, they all had telephones, and they all primarily supported Dewey. Well, as we know, this is not what happened, and there is a triumphant soon-to-be President Truman holding the newspaper. So it's been said there are three kinds of lies: lies, damn lies, and statistics. So which is it in your study, your client's Medicaid audit? Which is it? So the outcome of any study is determined by the characteristic that is sampled. So many of us were surprised by the outcome of the past presidential election. The polls seem to be all over the place, saying one thing, saying another. And there are many explanations for why that happened. And we've just listed some of them here: bias, a corrupted frame. Dr. Maykuth will talk about what a corrupted frame is. All sorts of issues which can't always be considered or are not always considered when a study is designed. Some polls are done for advocacy and not to answer the question. How the question is asked, very, very important. There's sampling error, there's response bias, all sorts of reasons why virtually all of these polls were not accurate. So ultimately, there's two questions in any study involving statistics. What is the it that is being measured by the study? And is the it being measured correctly? These are the key concepts. And it may sound simple, but you would be surprised how often it is not done correctly. So here's an example most of us are probably familiar with, the due date of a human baby. So the average gestation period is 280 days. We could generate, using a sample size of 20, a 90% confidence interval, and Dr. Maykuth will talk about what that is, would be between 273 and 287 days. That 280 days is a typo. It should be 287 days. So somewhere in that range, the 90% confidence interval has 7 days before 280 and 7 days after 280. Now the problem with this is only 40% of women give birth on the due date. So there's right away an accuracy error of 60%, inaccurate. You don't know the distribution, which is a non-normal distribution, and Dr. Maykuth will talk extensively about the consequences of having a non-normal distribution. And you don't know the conception date. This is something that's rarely known with any precision. So how believable is it to use this 90% confidence interval for the birth date of one person? And how useful is it to a person who wants to know what day the baby is going to be born? The answer is it's not useful at all. In fact, it's useless. It won't really tell you anything of any value. So again, we're back to the concept of the right idea but the wrong answer. So Dewey wins the election, but, well, not really. And we have our human baby due date example. Numerous other predictions based upon ostensibly statistical studies. We'd run out of oil in 13 years in 1939. The space program would have this catastrophic failure rate. So why are these studies failures? Because they're clearly not accurate. They have no predictive value. And the answer is they're not correctly designed for the question being asked. And that's what we're really trying to get at here, is that your client's Medicaid audit may also be incorrectly designed. So with that, I will turn it over to the nitty-gritty to Dr. Maykuth.
Thank you, Mr. Ross. Good afternoon, everyone, and thank you for joining us today. My goal in this session is to present some insights into the mechanics of probability sampling that may enable you to ask good questions about the statistics involved in overpayment calculations. I firmly believe that smart attorneys can grasp the higher-level statistical issues and be good consumers of statistics. I'll get a bit into the weeds in some of my explanations, but only enough to give you a glimpse of what statistics can and cannot do. While your gut instincts may be of little value in calculating probability statistics, they are very useful in informed consuming of the results. I hope the takeaway for you today will be that you feel that if something doesn't feel right, you look further in to see if it is right, and to have an improved sense of what questions to ask about audits and voluntary repayment studies. So what is statistics? The common definition of a collection and analysis, interpretation, and presentation of massive quantitative data doesn't get us very far. And I think we can go, it's nice, but it's not very informative for our purposes. We are interested today in probability statistics and using samples to estimate or predict the likelihood of the outcome from a universe of data. Numbers can be intuitively grasped and calculated arithmetically. The back of a napkin estimate can be pretty telling. But probability statistics have to be calculated on the base of the distribution of the data, the correct application of the methodology, and meeting the criteria of probability statistics. While they can improve the quality of decision-making, back of the envelope calculations are just numbers, and they don't measure with accuracy and validity. Probability statistics can only improve decision-making if correctly done. If statistics doesn't answer your question, it may not be the statistic's fault. Statistics don't answer all questions. They can't tell you who's going to be president, but they can tell you at a 95% confidence level, if the right people show up at the polls, who is likely to win. Consumers of statistics cannot afford to be intellectually lazy in evaluating the outcomes. If consumers manipulate the outcomes to address their questions, mistakes, errors, and misinformation almost inevitably result. A couple of terms just to get us on the same vocabulary. A universe is in these cases, a dollar amount paid to a provider in a specific time frame. The sampling frame is a subset of the universe that has been identified by universe limiting criteria, such as codes or departments or sites or particular providers. And it is the group of data from which the sample will be selected and over which it will be extrapolated. Sample is a randomly selected subset of the sampling frame to be audited for overpayment. And the unit of analysis is the it. It's the sampling unit, what is measured in the audit. Claim line, the claim, a beneficiary, a provider. And it must stay invariant throughout the study. So here we have doctor with his universe of provider paid claims, all of them. You go to the frame, and those are all claims of a particular time frame and code. You select a sample of 50, and the sampling units include a code and a time frame. And the individual claim in the sample must be in the sampling frame and must be in the universe. If something appears in a sample that isn't in both the universe and the frame, there's something profoundly wrong. This gets us to the basis of a corrupted frame. If you take the blue square rectangle as the universe and the oval-shaped sampling frame in the middle, the sample would be selected randomly from it, the pentagon-shaped sample. And you see this sample has some things in it that are outside the audit definition, outside the sampling frame, by date or maybe the right code. If you find something in the sample that's outside the definition, it's a corrupted sample. If there's something in the frame that's outside the sampling frame, and we find this a lot, I mean a lot more than is acceptable, and intuitively you know that you cannot select randomly something that doesn't exist within the frame or the universe. So we do get and see corrupted frames. Characteristics of a valid sample of an overpayment study follow along three basic levels. You have all the things that you have a prior history of overpayment, or a probe, or some measurement of error. And that's what allows you to start this whole process. You have a universe, and you define what of the universe you're going to look at to identify the frame. From the frame, after you've identified the frame, you look at the data in it, and you decide which inferential statistic method works for the rules. And then you go to sample selection, that's our second row, the sample definition, whether it will be simple or stratified. You calculate the sample size necessary. You select the seed and random number and apply the table of random numbers to an unbiased file that Mr. Ross was talking about. That should get you the basis of a probability sample if they are independent observations, randomly selected, normally distributed, and representative. You get a probability sample, and it's at that point and only at that point you go on to audit claims in the field. So what is a statistically valid random sample, and how does it help us? It's a guard against cherry picking and bias. It will meet the requirements of the methodology, especially the assumptions of the distribution. It will meet the chosen sampling error, what amount of mistake can you tolerate. It will be of sufficient size to accurately measure overpayments. It will be random and representative, meaning without bias. There's little guidance in Medicare and very little guidance in self-report information to talk about statistical sampling. The Medicare Program Integrity Manual, Chapter 8, has 19 pages of guidance for instruction for auditors to use in reviewing and calculating overpayment amounts to be recovered. Now, this is not a statistical treatise. There are no formula. There's no how-to. There's nothing about the rules and statistical standards. There's nothing about the specific statistical methodologies. But the MPIM does require that you have statistical expertise in design, oversight, and validation of the probability sample and the results. So it sends you to, while a guide, it sends you to the place to find information on the specific data set you're handling. Valid outcomes require proper execution of the chosen method. To attain a statistically valid result, I refer you back to the slide 28, which is the roadmap of the 3 layers of how you have to, what you need to do to get there. Properly defined universe, and it has to be produced. Define the sampling unit in a meaningful way so you know what you are measuring. Define the frame that contains everything that belongs there and nothing that doesn't. Use proper randomization. Produce a probability sample. Then accurately measure the overpayments. Meet the assumptions of the method. Use the correct formula for calculation. Do the math. Test the key assumptions for randomness, independence, normality, and representativeness. And accurately and truthfully report the findings. This tell the truth piece gets to be a little sticky sometimes. It's really harder than the checklist appears, but we'll explore some of the reasons why. Auditor's responsibilities. And these hold true whether it's a self-report audit or an audit review. You know the error rate by probe or history or industry norm. You supervise the selection of the sampling unit and choosing the methodology that's appropriate for the data. And there is no one-size-fits-all approach. Choose the right sample size, not something that comes out of a cookbook of 30 or 100. Test to see that it's representative and fits the methodology you're using. Exercise knowledgeable statistical oversight and quality controls. Document the process such that it can be replicated and then produce the documentation. Evaluate non-sampling errors and their impact. All studies have them. It's nice to know what they are up front. Calculate the results correctly and report them fairly. The audit design also has to meet the common sense test. When you read an audit as attorneys, you should be able to say, you shouldn't have to say, what the heck's going on here? You should have a pretty clear understanding of what has gone on in the study simply by what's reported to you. And then trust your judgment. If the auditor doesn't understand the claim, if it's a complex claim like a rug code and they're treating it like an office visit, if you have repeated physical therapy sessions, they need to be treated differently than individual emergency room visits. Again, the one-size-fits-all just doesn't work. Was the frame properly constructed? Is the sample random, representative, and large enough? And this last criteria you probably would need some help with, and that is, are the probability distribution points met? The rest of those you can pretty well get on your own, and with a little bit of experience you can start to get a pretty good feel. Do they match the probability idea? The probability of math doesn't change. The questions being asked can change, and the answers can be wrong. But in order to avoid silly mistakes, the study design has to make intuitive sense, and the methodology has to be properly executed. Each statistical methodology has a set of key assumptions that have to be followed for their use. Otherwise, the results are just numbers and have no predictive capacity. The most common statistic in these audits are point estimates, which is a type of mean, and confidence intervals. These are parametric statistics that require the four key things we've been talking to: independent observations that are randomly selected, normally distributed, and representative. These assumptions must be tested, and none may be ignored and still have a properly executed point estimate or confidence level. Statistically valid random sample. Random comes into play twice. Once in the selection of the random sample, and you have tests to show whether the result was random. And second is in the comparison of the sample mean to the frame. It comes into play as a measurement. The assumption is that overpayments across all audits will vary randomly. And in a particular audit, the sample overpayment will vary randomly as well. And if the findings are different from the random expectation, then what the expectation is you have legitimate overpayments, and that should be used for the basis of an estimation. In the first random sample, you have to be able, as Mr. Ross said, to replicate and test the sample. You need the seed that was used or provide the seed that you were using. You need the identical computer program, the identical input, what's the frame size, sample size, and did you ask for spares? And test to assure that there is both randomness and the appearance of randomness. Let's take a second on that. What's the appearance of random? It is possible to get a random sample of 30 that the first thing you select is 1, and the second is 2, and the third is 3, and so on till 30 in sequence. No one is going to believe that that was random, and if you test it, it won't show up as random. It'll show up as sequenced. So you need to test for the random. After you do your sample, you need to test for randomness and then for representativeness. I'm going to talk a little bit about sample size determination, and what we have here in front of us is the RATstats. RATstats is a suite of programs that CMS devised for easy use in these types of audits. It's quite a good one. They have a sample size determination program, and you will see there the inputs that you have to have. You need the universe size, the number of claims. You need the anticipated error rate, so that it comes from your probe or whatever it is you're using, your history or the history of that provider. You need the total amount of the frame, and you need the standard deviation of the frame, and then you can choose the confidence level and the precision levels that you want. And what you will get, based on these formula, the mathematical formula is at the top, but the words are in the bottom for a 10% precision and 90% confidence. So the sample size equals the standard deviation times the frame size squared divided by the 10% precision times the frame mean and sample size divided by 90, because that's your confidence level, plus the frame size times the standard deviation squared. It'll get you out of the fear of formula to the results. And these are the results for data that we put in. You see that RATstats produces an 80, 90, 95, and 99 because that's what we checked in the screen, and for a precision of 0 to 15. The most common confidence and precision level is the 90% confidence and the 10% precision. And if you go across to the precision at 10%, you will see 15 at the 90% confidence level. And then there's an asterisk. And RATstats tells you that this sample size is under 30 because sample sizes under 30 are considered small and are often not good for representative extrapolation, the likes of which you're doing here. We're going to go through what we mean when we're talking about with representative. A representative sample is a small and completely accurate picture of the data in the frame. It is a statistically accurate subset whose numerical membership represents the entire distribution of the frame. A representative sample is an unbiased indicator of what the frame is like, and representativeness can be tested mathematically. If the sample isn't representative, it's known as sampling error, and it's not going to give you accurate outputs. Here we have a picture with a frame picture with water, a boat, an iceberg, and sky. And so you see our sample picture is just a small version of it. But when it gets smaller, maybe we just want to know about the boat. So you could just pull out all of the boat data and analyze the boat. Then there are the iceberg, and if you want to know about the iceberg and the water and the sky and the boat, then you will put them into a stratified sample. They're all independent of each other. There's nothing in the iceberg that's in the sky, and there's nothing in the sky that's in the boat. So that's how you would handle the representativeness of the sample. If indeed you don't have any boat examples in your sample, then it's not going to be representative, and that's where you would kind of push for stratification to make sure that you took a sample within the strata. We'll talk a little bit now about distributions. Distributions are the probability yardstick. I'm going to go into the weeds here for just a moment as a basis for understanding the question statistics can and cannot answer. We know measurement tools like inches and miles and their metric versions. We know pounds and tons and their metric versions. We know ounces and pints and quarters and their metric versions. We're familiar with all of these as measurement tools. Though we may not be facile with all of them, we grasp how they work and what their relationships are. The measurement tool of probability statistics is the probability distribution, and we have little experience with them, even if you're math proficient. Just probability distributions are not part of what we have. Now I'm going to pull back a little bit out of the weeds, but not too terribly far, and discuss the underpinnings of the probability yardstick. In any audit, one sample of a chosen size is chosen out of a very large number of possible samples of that size, which could be taken from the frame. So a sample of 30 out of a frame of 400, you would start with, you might get a sample that goes from 1 to 30, claims 1 to 30, and the next sample would go 31 to 60, and the next 61 to 90, and then you go back and start 2 to 31 and 32 to 61. There are literally thousands of possible samples that can be pulled out of a frame, a sample size of 30. You can calculate the means of all these possible samples, and then that can be selected from the frame. It is possible to do this, and if you do this, it would give you the mathematical model of what is likely to occur if all possible samples in the frame were analyzed. In practice, if you take a large number of samples from the frame, a mean can be calculated for each sample. Each sample mean would not be exactly the same as the value of the others. Rather, the sample mean would differ one to another and differ from the true mean of the frame that you're trying to estimate. These means would be different from one another. However, they would cluster around the central value or the mean of the frame. There will be more scores in the middle of the distribution than at the ends, and the differences of the different samples are the basis of error that occurs when inferring from one sample in the frame rather than from measuring all the claims in the frame. If repeated random samples are taken moving on toward infinity or to the totality of the frame, their means are expected to fall into a normal distribution, and that's the central limits theorem which we in the field think is the holy grail. Let's use some examples here. Let's see if I can get my pointer working here. There we go. This is the frame in a somewhat normal distribution, and this is the mean of the frame that we're trying to estimate in overpayments. We'll start from right and go to the left. What we have in this sample here on the furthest most right is you see a mean that's quite distant from the mean of the frame, and it's a little bit taller and a little squishier. It's a little taller this way. The next is the mean is quite close to the frame mean, but the distribution, again, is taller and not quite the same. The third sample we've chosen has a broader, wider distribution, and the mean is further from the frame than the second one was, but not as far as the first. Now we come over here to the fourth example, and though its distribution is very similar to the frame, its mean is quite distant from the frame. So what do we know about this mean as an estimator? How accurate is it going to be as an estimator? Of these four samples, which estimates are we going to believe? How accurate the mean estimate of the four samples is at estimating the mean of the frame is the question, and the only question that probability statistics can answer. How accurate is the mean of the sample in estimating the true mean of the frame? Probability statistics doesn't tell you the dollar amount of overpayment, the birth date of an individual, or who's going to get elected president. They give the likelihood that the chosen sample accurately estimates the overpayment of the frame 90% of the time. And so reasonably you say, well, that's not good enough. Well, unfortunately, that's all you get. So it's sobering how poor an estimator a sample can be. If the mean of the sample is at the X mark here, it's probably not a good estimator, drunk or sober. The particular sample's information can easily be misused. The statistics aren't wrong. The application is wrong because the sample was not properly executed. If the consumer has to decide if it's accurate enough to be meaningful, then you have to test all of the assumptions of proper execution of the particular methodology. Most likely, the sample here at X is not going to be meaningful as an average mean estimation of the average of this frame. There's another complication. It's a bit of a sidebar, but it is a complication that is worth considering. The sample is selected from the amount paid to the provider. The sample is analyzed and extrapolated based on the overpayments of the sample after the audit. So you never know up front what the overpayment amount is going to be unless you know the history of overpayments and you can get an error rate. However, the actual overpayments you don't know until the end of the sample. So and there's another caveat that comes into this, if the overpayments are not correlated with the amounts paid, then the analysis should not proceed. That is, if the dollars in error are very small compared to the dollars paid, the statistics just aren't going to work properly. So if you have 15 or 30% of the sample dollar amounts in error of the amounts paid, the statistics are likely going to be wrong. And you're getting the point. It's much easier to get it wrong than it is to get it right. What's the big deal about the normal distribution? If the overpayment data in the sample are not normally distributed, the outcome of the sample extrapolation is going to be as inaccurate as the X on the drunk map. The normal distribution has many numerical qualities that make it enormously powerful mathematically, and is the basis of really the most elegant of the theorems of statistics, the central limits theorem, which allows you to do lots of things with that distribution that you can't do with other distributions. It's one of the few distributions where the visualization of the curve actually has some meaning and translates the math. So who cares? Well, we must care as long as the yardstick of the normal distribution is the most common one used in statistical analysis for these types of data. Now let's talk for a minute about important characteristics of the normally distributed yardstick. There are three things. When it's standardized, the normal distribution has 68% of the elements of the data within one standard deviation. Let's see if I can pointer going here. So between here and here is 68% of the data. When you go to the second standard deviation, it's 95.5% roughly that goes between this line and that line. And then when you go to the third standard deviation, you have 99.7 or 98% of the data will fall within these numbers. And your 90% confidence level is going to be somewhere right in here. The measures of central tendency in a normal distribution all fall right here. That's the mean, the median, and the mode. And just for a minute, the mean is the arithmetic average. The median is the middlemost number, the number of which half is above and half is below. And the mode is the most frequent real number. So if the most frequent claimed dollar amount is $87, that will be your mode. The normal distribution is symmetric. That is, you can take this 0 point, fold it in half, and both sides will be identical around the mean. If the payment data don't follow the overpayment data don't follow the normal distribution, then the accuracy of the sample for measuring the frame will likely be in jeopardy. The normal distribution is by far the most common yardstick distribution for continuous information like dollars that go from 1 to a number in intervals. If the mean overpayment of the sample is random, then you can calculate expected confidence levels using probability math. The sample mean overpayment is then compared to the theoretical yardstick of the normal distribution, and you can tell if the overpayments are by chance or whether they're real overpayments to the frame. All of this is weed stuff, and what does it tell you? Well, how do we translate what it does tell you? It tells me a lot, but what does it tell you? How do we translate these things into something useful to you and your client? And I think the first place to start may be the confidence level. Normality is a big problem for overpayment data when the frames are not normally distributed. And think about what the distribution of overpayments would look like when you had a bunch of non-overpayments. You had a bunch of claims that were correctly paid, so you get a whole column of zeros off on one side. So that doesn't get you very far. And it shifts the distribution. So if indeed you have a normal distribution, you can trust your confidence levels to be there and there. If you don't have a normal distribution and you have a whole stack of zeros over here, you might get a bimodal distribution, or this will get skewed substantially. You don't know what your confidence intervals will tell you. Let's look for a minute. The normal distribution here in the middle, you know where one confidence level is, where one standard deviation is. Two standard deviations in your 90% confidence will be about here in a two-sided confidence level. If you come here at this peaked or high kurtosis, it's going to be out here somewhere. It's going to be a little tougher. If you get this low kurtosis or a flat curve, and sometimes they'll get this flat, it's very hard to tell where your confidence levels will be. A right skew, it's almost impossible because you've got a mean here, and where is that correct percentage off to the side? Left skew's a little easier, but it's distorted, and when you're depending on this distribution to be your yardstick, this doesn't look like that yardstick. So this is an illustration, not mocked up data. And you see that the three levels of central tendency, the mode, the median, and the mean, are very far apart, not together. So why do you have a mean here at $1,274 and a median, the middlemost, that has 50% above it and 50% below it? Why are these so separate? Well, you look out here and you see you've got several claims, or some claims, at the $12,000 mark. They are distorting the mean and the median. They're separating them. And so it's a little bit like having a house in the same community as Bill Gates when you're talking about average housing costs. We'll move on to a set of real data and a distribution here. This is a nearly normal distribution. It's not quite normal because here at the $500 range or at the $50 range, you have far more claims there than you do in the rest, and so you've got some holes here under this, and you've got some excess here over the top. This is going to be dollar amounts, and this is going to be the number of claims at those dollar amounts. Here's a histogram of real data. It is, in fact, not bell-shaped. It is bimodal. Got a mode here, most frequent here, and a most frequent there, and they're different. And here in the middle, where you would expect the mean, there's not very much. So you've got a mode here and a different mode there, and then you've got stuff hanging off at the high dollar range on the right. If you were to take a random sample, you should know at the very beginning that this is not going to end up in a normal distribution. If you take a random sample from these data, and these are the numbers behind the random sample of this data, you find a mean of 430 and a median of 112 and a mode of 120. That's not normal. And then you have a standard deviation that's larger than your mean. So you're going to get a flat curve, very, very low kurtosis, and it's very far from normal. If you take those data and graph them, actually this is the graph of the overpayment of them. Let me go to the, sorry. This is the graph. I'll go backward to the actual data. You'll see that you've got a lot of zeros on the left-hand side. You've got some data chucked over on the right-hand side and nothing in the middle where your mean and other measures of central tendency should be. So these are the overpayment frequencies. You have a mean of $339, and you know from seeing the chart that there's nothing there. There is nothing at 339. There's nothing at 100, but you've got a whole bunch at the most frequency of 0. This is not a normal distribution, and it doesn't help. So let's talk about plugging these numbers in for your chosen for your confidence number. You want to get a point estimate. You have a mean overpayment. You have a mean overpayment you don't believe, and you multiply that times the frame size, and that gives you your point estimate. So then you want to get a confidence interval, and you take the point estimate that you've just calculated, knowing you don't have a useful mean, and it's plus or minus the chosen confidence interval. In this case, it's 90 times the sample standard deviation, the square root of the frame size, and so forth. But you see, if you get off at the very beginning of the point estimate with a mean, you're not, and you don't have a normally distributed set of data, you get garbage. And here's the output of this point estimate of $27,000, and what's going to be the demand amount, the lower 90% confidence level, is going to be $10,000. And then you go down to the precision percent, that's in red. And you have an inaccuracy rate, a precision percent, of 61, nearly 62%. What does that tell you? Well, it says 6 out of 10 times your answer is going to be wrong. You're right up there with estimating the accurate date of a birth. What do we believe then about the point estimate, which doesn't follow the normal distribution? What do we believe about that lower confidence level? Well, we know that it's simply an add-on. You add the confidence level, the total confidence level is the last line there, 33,556. If you split that in half, it gives you 16,778. You add the lower confidence level to the point estimate, and you get not what this picture says. The lower one gives you 10,368. The upper one gives you 4,925. Excuse the typo. But do we believe this $10,000 number? I don't. Do we believe that Dewey was president? Do we believe that the baby wasn't born on the birth date at which he was born? Is 10,368 an accurate estimate of the overpayment of the frame? It's not. It's a statistic. It's not a statistic, it's a number, because the key assumptions of the probability sample were violated. And it's not very helpful in making decisions. And here's what you see if you graph out the extension of the normal distribution past the $0 amount. It says that the amount of repayment should be negative dollars. So in this case, if the distribution were normal, the provider would be owed money, not the reverse. So just because you can calculate numbers and get an output doesn't mean that you have the right thing. Garbage in really does lead to garbage out. If a confidence level is off the charts, it's probably not a good one. Is it useful? No. Was Dewey president? No. So as counsel on these cases, you can help providers to be good consumers of statistics at the higher levels, well out of the weeds. But because you must demonstrate that an audit was invalid, or if you're doing a voluntary repayment, that the amount is valid, you must have the information to document what you did. Your clients must be able to demonstrate that they used valid statistics or that the auditor did not. The higher comprehension levels, if you feel it's not right, there's probably a good sense that what happened in the weeds isn't right either. The high-level understanding, you need to trust your gut and ask the questions that your gut is telling you. Sometimes, the question I get most often is it possible to use a sample size of 54 for this number? And I have to go test it, put the formulas in, and then you have your answer. Currently, Medicare and Medicaid auditors are stuck in a one-size-fits-all mode of data processing. They gloss over the very complex statistical requirements necessary for estimation, and then use some smoke and mirrors masquerading as probability statistics. When statistics are invalid or improperly executed, they should be challenged. If they are improper, they should be thrown out, and that makes a huge dollar difference whenever you can only reclaim the amount of the sample and not the amount of the extrapolation. So the one-size-fits-all is unfairness to all, but there are some places where you can make a difference. David?
Thank you, Dr. Maykuth. That was very informative. The bottom line on these issues are, I think you need an expert. You need somebody like Dr. Maykuth to take a look at what was done, because even the best intentioned study design can be flawed. And we've seen that even a well-designed probability statistic study can't answer the question that you really want to have answered. You can't predict who's going to be president. You can't tell what day your baby's going to be born. You can't tell the overpayment dollar amount for any particular provider. So what you can use these statistics for is that how likely is it that the mean of the sample that was tested, audited in this case, represents the true mean of the universe of claims for this particular provider. So that's all you can get, no more, no less. How likely is it? And if you're going for a 90% confidence interval and 10% precision, you better be prepared, if you're the state, to have an adequate sample size, because this is where we've seen the classic cookie cutter, assembly line, one-size-fits-all that Dr. Maykuth talked about. And, we've seen a sample size of 100 used for universes of claims that might have 900 claims in them, or even over 1 million claims. We've seen the cookie cutter come down, cut that cookie the same way no matter what the universe is. And they just don't want to move from that sort of one-size-fits-all approach. And there's generally reluctance on the part of the administrative law judges to get into the weeds, A, because I don't think they're familiar or intimately familiar with these issues. B, they're normally not raised by defense attorneys. And C, if you really take a hard look at what many states are doing, the conclusion could very well be that they're not doing it correctly. And as we've seen this in a number of Medicare contexts, they're not doing it correctly there either. And the result is, the extrapolation, this larger amount that is claimed to be owed by the provider, gets thrown out by the judge, leaving only the dollar value in error in the sample, which is typically minuscule and is something your client would quickly pay to resolve the case, because it's going to be a relatively small amount of money. So the goal in all of this is to get the extrapolation thrown out. And you look at the checklist of issues that we presented in the beginning. of the slides. These are the questions you need to ask, any one of which can be fatal to the government's position. And sample size is right up there as probably the most commonly disregarded requirement. And we don't see probe samples. We don't see error rates factored in. We just see the cookie cutter 100, sometimes 150, depending on which auditor's doing it. It's no more valid because it is just a different size cookie cutter. So there's rarely an individualized examination of the claims, the universe, the types of errors, the typical error in the community of that provider type. So it's all sort of a crapshoot, and it's presented to you, it's dropped into your lap, and you're forced to try to defend against this, and the presumption is against you. I mean, the presumption is that the state did this correctly, and there are many ways where you can show to an administrative law judge or other judge who's willing to at least be open-minded about these issues of whether or not this extrapolation should stand. And what we've said here has obviously absolutely nothing to do with the underlying claims. Whether or not they should be disallowed or not is not something we're talking about. We're assuming that the disallowed claims are in fact disallowable, and that is part of, there's an extrapolation and there's a demand made to repay money. If you're able to convince the judge that these claims shouldn't be disallowed, obviously the sample error is going to shrink and your extrapolation amount is also going to shrink. So we've just assumed that these cases involve legitimate disallowances. So there are many ways to challenge these things. Arm yourself with an expert, go forward, and we wish you luck. And the bottom line is, statistics in the hands of an inept auditor are like a lamppost to a drunk. They are used more for support than for illumination. So, good luck. And with that, we'll turn it back over to Molly for any questions.
All right, and I'd like to say thank you to Pat and David for your insights today. A brief announcement: New York State requires that you record and report the following code in order to obtain CLE credits for the live or recorded version of the CLE webinar. If you'll be requesting CLE credits for this seminar, please write this code down. The code is TLDHCJ. That's T like Tango, L like Lima, D like Delta, H like Hotel, C like Charlie, and J like Juliet. Again, the code is TLDHCJ. Now on to our live question and answer session. Listeners can ask our speakers any questions relevant to today's topic. You may email questions to healthlaw@stratfordpub.com. Submit questions by typing your question into the Q&A box at the bottom left corner of the screen and clicking send. You may also ask questions by telephone. To do so, press star 1 on your touch-tone phone. Again, that's star 1. If for any reason you decide not to ask your question, you can press star 1 again to exit the question queue. After you press star 1, and when it's your turn, the operator will announce the first and last name and the city for the person registered for your location. If you'd like to identify yourself further, please do so. And if you're asking a question by phone, please turn off the sound on your desktop. So our first question is, why is the Medicaid program trying to take back money for services rendered without any allegation of fraud?
I can take that. We've seen healthcare payors, Medicaid, Medicare, private insurance companies. They're all about recouping payments that have been made in many instances, if not most instances, for legitimate services rendered. And they're trying to recover these payments or recoup these payments simply because of some technical error in documentation or recommending the documentation contains certain things. The adequacy of the documentation, it could be present and just not complete or not as thorough as they would like. It's any reason to justify in their minds taking the money back. It's a technical compliance issue with documentation requirements. We've just seen this time and time again, so it's not unique to Medicaid. But even absent any allegation of fraud, and many times these auditors will frankly admit that the services there's no indication the services were not high quality, were not provided, there are no complaints. They still insist on having the money returned because of the documentation issue. So that's what I think is underlying many, if not all, of these recent Medicaid, Medicare, third-party insurance audits. And they just don't seem to be too concerned with the quality of the services. They just don't raise these issues. They just raise the technical compliance issue. So I think that's really the simple answer.
All right, and let's see the next question. Texas Medicaid divides audited claims, for example, pharmacy claims, into 3 samples: high dollar, medium dollar, and low dollar claims, in an attempt to prevent sample skewing. Can you comment on that?
I'll comment on that. It seems to me what you're saying is that they stratify or maybe do separate studies. I'm not sure which, but either one could be perfectly acceptable. So what we're trying to do, given all of this discussion about the distribution, what we try and do on the statistical end is to reduce variability, to get things that look the same into the same categories and take those things that are different into separate categories. So stratification is a very acceptable method. There comes a problem with stratification, though, and that's if the strata overlap. And that is, the dollar amounts may not overlap, but let's say you have diabetes supplies that build over, that you get monthly over a year. Well, if you have the same person, and let's say they're paid in three-month intervals. They're paid on 90-day intervals. If you have a 1 month in there for beneficiary A, and you have a 3 month in there for beneficiary A, and there's a price change, and you have another 3 month in there for beneficiary A, and they end up in different strata, you no longer have independent, non-overlapping strata. So I got into the weeds on that a little bit. Normally, stratification is a very good way of reducing variability, increasing accuracy with smaller sample size. It's why they were designed. You can get into trouble with independence relative to strata because they have to be non-overlapping and independent.
So if they had not separated these into these 3 strata, and everything was together, that's what would happen in New York. I mean, New York would never do anything like this sophisticated in my experience. So what would happen to the distribution? It would just become a mess, wouldn't it?
Well, it's a little bit like the example I gave. If there had been a third blip in the frame example where it was a bimodal, you'd have a trimodal, and then your mean would be equally meaningless. You get this big dispersion and not the normal bell-shaped curve.
So it would my lay interpretation, I would call that a mess.
Gotcha. You're absolutely right. What would happen is that the lower confidence level would get even lower. And where in my example you were wrong 6 in 10 times, you might be wrong even more than 6 in 10 times. So yeah, that's a mess.
I see. Okay.
All right, another question. Are you aware of any reported decisions rejecting RAT stats extrapolations?
If the question is rejecting the use of RAT stats for the random number generation, I think the answer for me would be no. If they're going to be rejected on another basis, I would ask Pat if she has any experience with that RAT stats and the non-randomization piece would ever be the basis of a rejection.
RADstats is a suite of programs, so they have things like random number generator, sample size determination, variable and attribute appraisals, which are estimation programs. I have never known any valid methodology to be rejected. I have known improperly executed RADstat outcomes to be rejected, and my example really is an invalidly executed RADstat. I use RADstats for all of the backup there. So it's not, if the methodologies within RADstats are well documented, well understood, well researched, and have been out there as kind of the cook's recipe rather than the chef's recipe of how to do these programs. Now that doesn't mean that just like putting those bad numbers, ignoring the distributional requirements of the methodology, you can't get outcomes that are rejected, but the statistics are not rejected. Now you could RADstat's variable appraisal program requires a normal distribution, and if you could easily reject the outcome because the key assumptions weren't met. It's putting diesel in a gas engine. You know, it'll go for a minute, but then you'll pay for it.
Okay, because I mean, RADstats has been officially adopted by the Federal Office of the Inspector General, so it wouldn't be a problem with the program. It would be a problem with what the user was trying to do with the program.
You know, certified by the National Bureau of Standards in the late 80s. The programs themselves are solid, but as you say, you can get that wrong.
Okay. Good question.
All right. Another question. In your experience, what arguments have been successful in contesting these types of audits?
We've seen in New York, it was a powerful argument when it was made that the source code used in the random number generator computer program was not provided to anyone. So the provider was unable to test the source code. So if you're in a state where there's a computer program being used to generate the random numbers, and it's a proprietary product, or it's not certified, by anyone, or it's not widely used, these are the best. I think you have a very good chance of convincing a judge that, it's not necessarily under the Fry test, but if it's not scientifically reliable in other venues, why should it be accepted in the venue that you're in? Would be the argument I would make. So that was very effective in New York. We have made arguments regarding the source code and what it actually did, and I touched on this earlier with our expert in one particular case. It was successful in only preserving the issue for appellate review, were we to go beyond the administrative law judge level, because there was sort of an institutional bias there against sort of really questioning the heart of how New York does its Medicaid audits. But we preserved that issue for appeal, and I think at least in part because we did that, we were able to obtain a favorable settlement. So in many times you're not able to, entirely throw out the extrapolation, but you can do enough damage, and maybe before the judge decides the case, arrive at a more favorable settlement because of just the issues you've raised with the process. So, Pat, I don't know if you can add anything to that.
I think so. We've had judges and adjudicators seem to understand that because the burden of demonstrating that the burden of proof switches to the provider in these cases, it is assumed that probability statistics are real, and in order to prove them wrong, you have to show that they were invalidly executed. So if you don't get the documentation, you don't get the universe, you don't get the random sample in the process, or there's a corrupted frame, and I call all of those documentation problems. They're more than that, but that's the categories. We've had very good experience in many states and at the federal level with having extrapolations thrown out on those bases. Almost every adjudicator I've ever bumped into, if you can demonstrate that it wasn't a random sample, will back down. If you can demonstrate that the frame was corrupted, that somehow something miraculously got into the sample that wasn't in the universe, or maybe wasn't in the frame, those fly pretty well. When it comes to the actual probability statistic stuff, what I'm seeing right now in Medicaid cases is what we've been seeing in Medicare cases for a long time, and that is you convince the ALJ that the numbers are just about as bogus as they could possibly be, even though they're numbers generated by a program. And then there's a very hardy negotiation that radically reduces. They may not throw out the whole thing, they may not invalidate it, but that has been successful in our experience in many states, and is being quasi-successful at the ALJ level, the Medicare ALJ level.
All right, another question. On slide 42, why is the sample a replica of the whole iceberg and not just a piece of the ice?
That's a very good question, because it depends on what the it is you're looking at. In that example, I was thinking of it when I made it as an example of a stratified sample, but if you want a stratified sample, then you would use the individual strata, the boat, the ice. They would be separate, and you'd only be picking from them, so you'd be sure to get the right proportion. Your sample size determination would allow you to get the right proportion. If you only wanted ice, then I would suggest you just pull the ice out and don't fool with the rest. If it's going to be representative and it's a simple sample where it's not divided into parts, similar parts that are non-overlapping, the reason your sample should not be all ice, because your picture isn't all ice. And if it's going to be representative, then it needs to be representative of all the pieces.
All right, another question. What programs are used to get random numbers?
Well, one program that's being used in New York State, it's called Wolfram Mathematica, which we know little or nothing about. We've made Freedom of Information Law requests to the state Medicaid agency and essentially wound up with nothing. So we don't know much about that program. RADstats, as we've already discussed, very well established. Pat, have you seen other random number generators used?
Almost every big statistical program, BMDP, SPSS, SAS, have multiple random number generators for multiple things. And each of those have at least one, and many have two or three, where you can set the seed or retain the seed. So it's important to be able to set it, because if you want to replicate it, you've got to be able to put it back in. And that's what New York isn't doing anymore. They've saved the seed, but you can't put the seed back in the program, so the seed is of no value to you.
Sure.
And the seed is because these are pseudo-random numbers, they're not absolute random numbers. You have a start point, and then there's some sequence, some algorithm by which a random number is selected, and every time you put the same seed in the same set of data, you get the same answer. Well, if you can't do all of those, if you can't retain the seed and re-enter it and get the same output, then you can't replicate it. So all major programs, because in science it's assumed that if you cannot replicate the random sampling process, it isn't random. That's just the standard. You must be able to do it. How these audits manage to get away from that standard is well beyond me. But there are plenty of ways, some free, some proprietary, to get legitimate random samples, and as long as they're replicable using the same process and are part of a package that is big enough to have been tested over years or over volume, you'll be fine.
So really that's the key to the scientific method, right? You have a hypothesis, you conduct an experiment, and you replicate it. So absent the replication, you don't have science, or you have potentially an arbitrary, biased outcome by the audit. So another thing I wanted to add is that New York, once for many years, probably 20 years or maybe longer, used a proprietary program which had sort of inside it the workings of another program, and that was Oracle Corporation's random number generator. So this program was created by a vendor who took Oracle's program, which I think might even be freeware, and put it inside a program that he either constructed or designed or had somebody construct or design it, and then manipulated in various ways the outcome of the Oracle program. So you don't know until you have somebody look at it whether, if someone's done that, if someone's nestled another program within another one, you don't know whether it's working correctly or it's operating as its designer intended. So that's really question number one, looking at these, the various states, what was the software program that was used? And you may find it hard to believe that freeware like RatStats is not being used by many states. And they're using things which are subject to challenge and readily challengeable. After an expert reviews, you've got to go to the computer source code level and see what the program is actually doing to the numbers that are being generated.
All right. Another question. Could you elaborate on the test for normality? When you test for normality, is that conclusive? This is tested as a matter of course?
I'll let you handle that one.
Okay. A test for normality is a probability test, and we spent the last hour talking about the believability of probability testing. But this is a pretty straightforward one. How does the data set you're looking at compare with normal? And it's a pretty straightforward test, and if it's not normal, then how not normal is it? Well, if it's significantly not normal, where significance starts at 0.05 and gets more significant as the number gets smaller, so 0.05 is where you start, but 0.01 is smaller than 0.05, and 0.001 is smaller and more significant. So once you get to the tests of significance, that's where you say it's significantly not normal. Being just not normal sort of doesn't matter, but once you get to those levels of significance, they are reliably not normal. Multiple tests will show the same thing. There's more than one test. There are 2 or 3 that are common, but there's more than one. And they're quite reliable, and you have to do something else other than the parametric statistics that are used here. There are other ways to accomplish the same thing mathematically as lack of normality, and that would be to do something like a transform. Sometimes a log transform works. It doesn't work with these data. But if you transform the data into something that acts mathematically the same way a normal distribution does, then you can get there. The math on it is, although complex, is pretty accurate, reliable, and repeatable.
And one thing I'd like to add, we've seen a number of instances where the state generated a set of random numbers, subjected those numbers to tests for normality, and for various reasons they did not pass those tests for normality, so they generated another set of random numbers. So it's very interesting that even using computer software, it can produce ostensibly a set of random numbers unique to that particular seed, yet those numbers don't pass the test for normality. So that's a very, to me, sort of, I thought I really had a firm hand on all these issues with the computer software, and then I saw that happen. I was like, how is that possible? How does the software fail to generate a set of appropriate numbers?
I think the example I gave sort of speaks to that, where it is entirely possible to generate not probable, but possible to generate a sequence of 30 numbers, 1 through 30, randomly. You're not going to do it twice, but it's entirely possible to do it for that to happen. Well, a test of random numbers would say those numbers have a pattern. They're not, even though they were randomly generated, they have a pattern. They're not random.
And those tests will discern some implied or underlying pattern?
Absolutely, that's what they do. The easiest one is the runs test, and it comes out of manufacturing, where they're looking for something that deviates from random for mistakes in manufacturing.
All right, another question. How often does the government get it correct?
Yours, David.
Well, speaking primarily from Medicare and Medicaid in New York State, I would say they've never gotten it correct with respect to sample size, not even once. And we've seen just so many different issues ranging from miscalculation errors or corrupted frames that there are some audits which have only, in my opinion, based on consultation with experts, only a sample size issue, meaning that the only thing that they got wrong was a sample size that was invariable and too small. But if you assume that to be acceptable, and it's not, that the rest of the process seemed to follow suit and was replicable. But there are times where we see, nothing done correctly. And Medicare is even more fertile ground for a more diverse set of problems than Medicaid. So I would say just not very often.
I would agree with you, and I think part of the index of that is when you look at the statistics that came out of the ALJ hearings and how often there are errors in each level of appeal in Medicaid. You're up there at 70-80% of the time they're throwing stuff out, so that's not a very good get-it-right rate. I think where they get it wrong the most, and it's where when you're doing, it's a little bit frustrating when you're doing voluntary repayment because sometimes the state entity that's looking at the repayment wants you to do the bad process. And it's the methodology. The methodologies they've chosen don't fit overpayment data very easily. It's not what the RATSTATS programs were designed for. They were designed for a different style of thing. But even if you do it right and more accurately, sometimes the state repayment folks don't want to hear it. So you can get it right, and as far as they're concerned, that's not, I've got states where they won't let you do a stratified sample. Well, that's kind of silly.
Well, maybe in the end that's helpful to the client, if in fact the confidence interval is wider, and maybe in the end it's helpful that a lack of imprecision is helpful. The statistician in me finds that an unacceptable answer. If you're more wrong and it's to my benefit, it's right. No, you don't get to use the extrapolation when it's that far.
All right, so since we don't have any other questions, I'd like to wrap up and say thank you. We hope you have enjoyed our national webinar, Medicaid Audit Overpayments, Challenging Statistical Sampling and Extrapolation. If your question was not answered, you may email it directly to our presenters. Their email addresses are included in the presentation materials. If you're seeking continuing education credit, you must verify your participation in this webinar by completing and submitting this attendance affirmation evaluation after the program. A link to this form will be included in the thank you email that you will receive immediately following the program. As long as you have registered and paid for this program by 5 p.m. today, you will receive your certificate of attendance within 24 hours. If you have any questions about continuing education credit for this webinar, please call our continuing education department at 404-881-1141, extension 35. Today's participants can order a recorded version of this event at a special attendee price. Please call customer service at 800-926-7926, extension 10, or visit Stratford's website at www.stratfordpub.com. Please be sure to check Stratford's website for information on future Stratford CLE programs, including a webinar on medical necessity documentation, challenges and defense complying with federal and state regulatory requirements, demonstrating reasonable and necessary health care services, on Wednesday, March 22, 2017, starting at 1 p.m. Eastern for 90 minutes. Stratford would like to thank you for your attendance. To end this call, simply hang up the phone. Thank you and goodbye.